Okay, so for this experiment, benzocaine was synthesized and it was completed by myself, Alyssa Midstarfer, and my partner was Ben Esquivel. So I'm not going to read the abstract word for word, but basically benzocaine was the ester derivative that was formed. This was found through IR spectra analysis, and then the percent yield was found to be 17.43%. And the melting point was 87.2, and then I'll get to why these values were slightly off of the true values a little bit later. So a little bit about benzocaine. The actual name for it is ethyl 4-aminobenzoate. And as I mentioned before, it is an ester derivative. In figure 1, you can see the ester structure, general structure. And esters are found in pretty common places, a lot of fragrances, essential oils, glycerides, which are essentially lipids, DNA, it's found in the backbone of it, and polyesters form plastic. It works as a topical agent. Benzocaine works as a topical agent. It's a local anesthetic, and it numbs the immediate area on the skin by blocking the nerve signals. Therefore, it's used to treat pain-related issues like sunburn, sore throats, earaches, and a lot of others. In figure 2 on the right, you can see the actual structure of benzocaine. You can see the amine group, the aromatic ring, and the ester itself. Benzocaine can be formed using Fischer esterification. This process forms esters from carboxylic acids by treating them with an alcohol and an acid catalyst. Water is formed as a side product in the end, and the acid catalyst is regenerated. In the figure below, you can see the key bonds that are formed and the key bonds that are broken throughout the entire Fischer esterification process. A little bit more about esterification. It is a reversible process, which can be a potential issue. We can utilize Le Chatelier's principle to counteract this reversible property of the esterification. One way to do this is to use the alcohol in excess, and that's by using it as a solvent and a reactant. In this case, we did use the alcohol as both a solvent and a reactant to increase the yield of benzocaine. We also did use a dehydrating agent. In this case, it was sulfuric acid, which also happened to donate the proton to the carboxylic acid to start the whole esterification process. And then another way to remove water besides the sulfuric acid was to use physical means, which would be heating or distillation. And in this case, it was heating under reflux. So here's the actual mechanism. So you can see up in the top left that the carboxylic acid grabs a proton from the sulfuric acid, the acid catalyst. It forms an ion that the alcohol then attacks. This forms the first tetrahedral intermediate. This tetrahedral intermediate reacts with water and forms a second tetrahedral intermediate. And essentially you get your ester with the acid catalyst reformed, and you do get some side product of water. So more specifically, the benzocaine synthesis, you can see that the p-amino benzoic acid is reacted with ethyl alcohol, and sulfuric acid is used as the acid catalyst, and you eventually get your benzocaine molecule. And the overall purpose of this experiment was to use acid catalyzed esterification to synthesize benzocaine. So the experimental methods, this looks scary, but essentially we added p-amino benzoic acid and ethanol to a conical vial. We then added sulfuric acid dropwise. It was heated under reflux for 20 minutes. Since the solution didn't clear up right away, more ethanol and more sulfuric acid were added. The reaction was then again heated for 45 more minutes. It was placed in a beaker with water, and sodium bicarbonate was added until the pH was around 8. The crude benzocaine that we obtained at that point was collected via vacuum filtration and then rinsed with water. We air dried and weighed that and then transferred it to a flask for purification with methanol. Water was again added, and the pure benzocaine was weighed. The melting point was eventually obtained. Percent yield was calculated, and the IR spectrum was found. So our results, so the grams of crude product that we ended up getting was 0.054 grams, and the grams of pure product was 0.042. So obviously there's a little bit of mass loss somewhere in there. The actual melting point of benzocaine is 88.9, and then the experimental melting point was 87.2. And down there on the bottom, you could see that this is figure 3, actual IR spectrum of benzocaine. You can see it around 3,400. You can see the peak for the amine in the actual IR spectrum. You have another peak for the amine at around 800. At around 1,200, you do have a peak for the ester. And then at around 1,500, you do have a peak for the aromatic ring. What I just said is reiterated on this slide. And you can see that each of these peaks at 800 and 3,400 for the amine are both present in the experimental IR spectrum, which is shown here. This is the amine group at 3,400 is important. The peaks that are there, these peaks are kind of sharp, which indicates that water really wasn't a huge factor in our product, which is a good thing. If the water had been present, the peak would have been more broad and the percent yield and the melting point would have been farther off. And then to the right, there is a figure just again reiterating which functional groups we should be looking for within the IR spectrum. And you can see A is the amine, B is the aromatic ring, and C is that ester again. So how I calculated percent yield, I found the theoretical yield by determining the limiting reagent, which was p-aminobenzoic acid. The 0.241 grams was the theoretical yield. I took the yield that I obtained, 0.042 grams, divided it by 0.241 grams and got a percentage of, and multiplied by 100, and got a percentage of 17.43%, which is a little bit lower, but I'll get to why that is in just a second. So, in conclusion, the IR spectra analysis indicates that this experiment was a success, as all the peaks that are present in the actual IR spectrum are present in the experimental IR spectrum. So that tells me that benzocaine was actually formed. And the melting points were slightly different. Our melting point obtained was 87.2, which was kind of close to the actual melting point of 88.9, which again further reinforces that benzocaine was most likely the product that was obtained. And then the percent yield was 17.43%, which is low. This could have been due to a number of things, but the most important that stuck out to me were a mass loss that was that occurred when we were transferring the product, the pure product from, well, both the crude and pure product, I suppose, transferring from the filter paper to the watch glass. Some products still stuck to that filter paper, so that loss of mass could have contributed to a lower percent yield overall. And then at the stage where you had to add sodium carbonate to induce crystallization, it could have been that the crystals were not given enough time to form. We probably could have made a little bit more product had we let it sit longer or stirred a little bit longer or scratched the glass to induce crystallization, whatever the case may be. If the experiment were to be completed again, I would definitely be more patient in my heating process, making sure all of that solid was dissolved out of that vial and then, or dissolved into the liquid in the vial, I should say. And then again, I would give the crystals enough time to form. That way I got the maximum amount of product I needed to create the highest yield possible. And that is a synthesis of benzocaine.